Hey guys, we're going to learn section 1.4, continuity and one-sided limits. So what we are going to accomplish, we will determine continuity at a point. So I'll give you an x value and we want to see if the function is continuous there. We will also determine whether the function is continuous on an open interval. So that's like from one x value to another x value. Is your function continuous? After that, we will talk about one-sided limits, which we've talked about in class before already. And we will also do continuity on a closed interval, which is from one x value to another x value, but we include endpoints on closed. Open intervals, we do not include endpoints. Here's our assignment, pages 79 to 81. All right, continuity at a point and on an open interval. For a function to be continuous, it has to be unbroken. So what that really means is that there's no holes, jumps, or gaps in your graph. In other words, you have to be able to draw the graph of the function without picking up your pencil. So let's focus down here on number 1. These guys will be examples of non-continuous graphs, which is also called discontinuous. Okay, so to start off on this guy, we have f of c is not defined. Not defined means that for that x value, there is no y value. There's no actual point there. So we've seen pictures of this before. A hole in the graph at x equals c would mean that your function is not defined. Okay, that's where your denominator equals 0 and your numerator also happens to equal 0. Second option is vertical asymptotes at c. This is where your denominator equals 0, but the numerator is some other number. Okay. Move it on to the next guy, where your limit does not exist. We have a couple options for this one as well. Vertical asymptotes would cause limits to not exist. Also, limits do not exist when the left side and the right side do not match up. You can see that this function is not continuous because you follow here and then you have to jump and pick up your pencil to be able to draw the second half of that graph. And number 3, where the limit as x approaches c of f of x does not actually equal f of c. So this means that the two sides go to the same spot. Okay, your limit exists when you have a hole, right? Left side and the right side go to the same spot. But f of c, so that y value, is not actually at the spot with that hole. Okay, so this would be a non-continuous function because you draw, then you have to pick up your pen, draw this point, and then start back here and go this way again. Examples of continuous functions. Straight lines, like linear functions, are continuous. Squared functions like y equals x squared, totally continuous, x cubed. So any polynomial is going to be continuous. Okay, the definition of continuity. So for your graph to be continuous at a point, which means continuous at c, some kind of an x value, we have to have 3 conditions. So when I talk about the definition of continuity, like use the definition of continuity to prove that your function is continuous, we are going to have to go through these 3 steps and you have to go through them in order. So the first thing you have to look for is f of c is defined. Okay, so there actually is a point. Okay, we had that issue here and here where there was a hole or a vertical asymptote, which would make f of c undefined. Okay, continuing down here, number 2, the limit as x approaches c of f of x exists. You have to actually have a limit. So the left limit equals the right limit. Okay, we did not have that here on number 2. The limit did not exist here because of the vertical asymptote, and over here the limit did not exist because the sides did not match up. Then number 3, the limit as x approaches c of f of x has to actually be filled in. We're allowed to have limits with holes, but this point would have to actually fill in the hole, so that would equal f of c.